Today. We're so pleased that the media has expressed such interest in the story of our solar sailing spacecraft's test mission, and we're really pleased that you can join us today for this update as we've reached a landmark for our test mission as a precursor to our next mission, which is set for 2016. Before I get started with some introductions, I'll state that my name is Erin Greason. I'm the Communications Director at the Planetary Society, and I'd like to run through a few rules of the road for our press conference today just to make sure that everything goes very smoothly and we're able to answer as many questions as possible. So to start, if you can please mute your phones as well as your computers throughout the press conference today, that will ensure smooth sailing. Please be sure to unmute your phone when you have a question during our Q&A period. Our format for today is a half an hour of presentation time. So you'll enjoy listening to our presenters at that point, and subsequently we will have a 15-minute phone Q&A period. At that time, if you have a question to pose, please state your name, and I will help to facilitate your question. If you have a specific target for your question, please state the name of the spokesperson who you'd like to ask the question toward. Afterward, we will have about 10 minutes of Q&A leveraging our Twitter Ask Planetary hashtag. So we also have a chance to fold in some questions that we're gathering online. And then we will wrap up on time. And if you did not get your question answered today, not to worry. Go to our website, planetary.org, into our LightSail press room, and we have a wealth of media resources that you can use there for your reporting needs. And we're also always pleased to set up interviews with our spokespeople if we don't have time to get to all of your questions today. It's really important to us that we are able to answer your questions. So without further ado, I'd like to first introduce our presenters today and then run through the list of other experts that we have on the line to answer your questions. We have Bill Nye, also known as the Science Guy, who is the CEO at the Planetary Society. We also have Dr. Jim Bell on the line. Jim is the president of our board of directors at the Planetary Society, and he is also a professor at Arizona State University, the School of Earth Science and Space Exploration. We also have the LightSail project manager on the line, Doug Stetson. Doug is president of the Space Science and Exploration Consulting Group. In addition to these presenters, we have several experts for your Q&A period. Rex Reidenauer is the CEO and president of Ecliptic Enterprises Corporation. We also have Barbara Plant on the line today. Barbara is president of Boreal Space. I'm also pleased to present Jennifer Vaughn. Jen is our chief operating officer at the Planetary Society. And you are also probably familiar with Jason Davis. He is our digital editor and the embedded LightSail journalist. You've probably been following Jason's tweets. I'm also very pleased to note that we have an undergraduate student who's involved with the LightSail project on the line today. Kevin Okseniuk is a student at the Georgia Institute of Technology. So as you've been following, LightSail reached a major landmark this week. And I would like Dr. Jim Bell to kick off an introductory period here to speak a bit about the history of the Society, and then we will segue into our other presentations. Jim?
Thank you very much, Erin. Can you hear me okay?
Yes, we can. Thank you.
Great. Thank you so much, and thank you, everybody, for joining in this morning. This is such an exciting day and such an exciting time for the Planetary Society, our members, staff, board, and our just amazing spacecraft team from Cal Poly, Georgia Tech, Ecliptic, and other supporting organizations. It's a really exciting time. Just to remind you all, the Society's mission is to empower the world's citizens to advance space science and exploration. That's exactly what we're doing. We've got more than 40,000 current members worldwide. More than 500,000 people have been members over our 35-year history, and hundreds of thousands more people are associates who currently follow us on social media or access our website. And so we work to create, advocate, and educate. That's our slogan. And this LightSail mission is a great example of one of the projects that we use to achieve those mission goals. That's to just very briefly frame the history of solar sailing. And the idea of sailing on sunlight goes back many centuries, many centuries. Indeed, the astronomer Johannes Kepler thought it was a plausible way to travel in space And he wrote in a letter to Galileo, quote, "Provide ships or sails adapted to the heavenly breezes, and there will be some who will brave even that void." So it goes that far back, and probably even dreams before then. But it wasn't until the 19th century that physicists like James Clerk Maxwell showed that light, including sunlight, has energy and momentum, and you can use that to impart force to other objects. And Maxwell didn't necessarily have solar sails in mind, but rocketry and spacecraft pioneers began thinking very seriously about that possibility in the early 20th century. One of those pioneers later in the 20th century was, of course, Lou Friedman, one of the co-founders of the Planetary Society, along with Carl Sagan and Bruce Murray. And sort of buoyed by Carl's ability to excite and engage the public in science and exploration, and you'll hear more about that shortly, Lou led the Society's first solar sailing effort, which was called Cosmos 1. It was a small spacecraft designed to deploy and test a large solar sail in Earth orbit in 2005, going up to an altitude of about 800 kilometers. And up at that height, the atmospheric drag would be negligible, and so we could demonstrate the ability of sunlight to guide the propulsion and navigation of a spacecraft. Unfortunately, a rocket failure prevented the spacecraft from reaching orbit, so that mission was not successful, but still Lou's and our society's dreams of solar sailing did not fade away, absolutely. And indeed, there's a current revolution going on in small and relatively inexpensive spacecraft called CubeSats and other very small spacecraft that have provided an opportunity for us to restart that effort. And in 2009, I believe it was in the celebration of Carl Sagan's 75th birthday, in memory of his birthday, the Society announced plans for a project called LightSail, this new, leaner implementation of our efforts to demonstrate solar sailing. We had a lot of member enthusiasm and very generous funding from our members. They made it possible to make this a two-stage process. First, we'd launch a LightSail test flight to low Earth orbit to work out any bugs in the spacecraft and the deployment systems and the instrumentation. And we knew this mission would be relatively short because atmospheric drag would cause the sail to re-enter the atmosphere relatively quickly from such a low orbit. But it would be a test mission, and if it succeeded, it would pave the way for a follow-on LightSail primary mission next year to a high orbit like the one planned for the original Cosmos 1 to truly sail on the solar wind. So that's a little bit of the history of this project and of our organization. And now to tell you a lot more about the mission of LightSail and the Society's larger goals of enabling solar sailing as a viable means of propulsion in the solar system and beyond, I want to turn it over to our CEO, Planetary Society CEO William Sanford Nye, also known as Bill Nye, the science guy. Take it away, Bill.
Thank you, Jim. Thank you indeed. Hey, everybody. Thanks so much for taking the time. I am so excited because this mission is a success. We were able to launch. First of all, we were able to qualify to launch. Now, we are a nonprofit organization funded entirely by members and supporters around the world who think space exploration is a worthy use of our intellect and treasure. And we qualified to get on a great big rocket, and that was 5. So you got to pass vibration tests, you got to pass thermal tests, heat and cold especially, and you got to be in a vacuum. And we did all that. Now, it's interesting to note that there is no thermal vacuum chamber in the world big enough to hold all 4 of our sails, even though they came out of a very small box, the NASA standard called a CubeSat, which is 10 centimeters by 10 centimeters by 10 centimeters. But ours is a 3-unit or 3U CubeSat, so it's 10 by 10 by 30 centimeters. And that sail deployed, bigger than most living rooms. And so we're very pleased because the sail really did deploy, and we got some very nice images, and one so far that just really has my heart. It's beautiful. And this goes back for me all the way to the disco era. When I was in Carl Sagan's class, I'm a mechanical engineer, and I took astronomy as an elective. As a senior in college, I took a freshman course. My dad was very interested in astronomy. He had been a prisoner of war and had very dark skies for many years, and just was fascinated with the stars. And so I took his class. I thought it was interesting. Well, he talked about solar sailing in 1976 and 1977. And if you've seen our website, we have video of him showing a model of a solar sail spacecraft to Johnny Carson. Now, that model resembles our LightSail so very much because we solve the same engineering problems. How do you deploy a large sail in space? How do you hold it rigid? And we had to solve the same problems, and so far we have. Now, that mission that Carl Sagan showed Johnny Carson was the Comet Halley mission. It was going to catch up with Comet Halley, which you also, some people call Halley's Comet. But that mission was canceled for budgetary reasons and this and that. But the people who were involved, Lou Friedman and Bruce Murray, who was the head of the Jet Propulsion Lab at that time, and Carl Sagan, they founded the Planetary Society. I joined in 1980. I've been a member ever since. And so we are fulfilling at least a 39-year-old dream. And it's really, it just means a great deal to me. So solar sailing is worth doing because it has the potential to democratize space. It will allow small organizations or organizations who don't want to allocate too much money to a space mission to build a small solar sail, deploy it the way we deployed ours, and go to, well, you can pick almost any destination in the solar system. If you have time, you can get there because you never run out of fuel. The sun shines all the time. And by the way, what we rely on is photon pressure. This is the momentum of light itself, of the photons of light. It's not the solar wind. The solar wind at its biggest is about 1/100th of the pressure, the 100th of the momentum of the pressure of photons, and a lot of times it's substantially less than that. So it's the light pressure that carries solar sails farther and deeper into space. And this mission was not without trouble. I'm sure if you were following it, a couple of just really, really unforeseen and very troublesome problems came up. But I'm an engineer, but the people who solved this are just extraordinary engineers, and they were able to figure out very diligently this subtle problem with the software, and they made it go. And so I'm just very, very proud because we at the Planetary Society, since the early days, have been charged with engaging people around the world in the exploration of space, to advance space science and exploration. That's our mission, to enable citizens of the world to know the cosmos and our place within it. And the LightSail program is consistent with that. This mission is part of our mission. And so now I'd like to hand it over to Dave Spencer, who is the mission manager on this project and just pulled off some extraordinary work. So here you go, Dave. Thanks.
Bill, thank you so much for that presentation. I would like to introduce Doug Stetson, our project manager.
Okay.
Doug is on the line today. Dave is unable to make it today, but we're so pleased to have Doug Stetson on the line to provide a presentation about LightSail, the test mission, and the 2016 mission. And Doug will be a great spokesperson to provide reporters with an update about what we learned on the test mission and how that applies to 2016. Thank you, Doug.
Well, let me just say, I'm sorry. We were going to have Dave, but Dave is working on the downloading images right now. So the overall manager is Doug Stetson. He's going to talk now. Sorry about that.
Thank you so much, gentlemen. If I can please remind everyone on the line to please mute your phone and your computer if you're not speaking. Thank you so much. Doug?
Okay, yeah, thanks a lot. And thanks, Jim and Bill, for the introductions. As you can tell, those guys are awfully excited about the LightSail project, and so is the entire technical team. So my name is Doug Stetson. I'm the LightSail project manager, and I'll give you just a brief summary of the current status of the mission and the spacecraft, and a little bit of insight into our goals and plans for the primary flight coming up next year. So, as you all know, we've passed a number of milestones with LightSail over these last just about 2 weeks. The most important of those milestones were just last Sunday when we deployed the solar sail, And then finally yesterday, when we were able to downlink the full image, confirming that, in fact, the solar sail was out and looking good. And actually, I'd say the solar sail is looking great. I mean, we just could not be more pleased with the way it turned out, especially after all the ups and downs that this project has been through. So to see that image come down the way that it did, and the sun in the background, was just very moving, and the entire team is thrilled about it. So basically, what that image does is confirm that the solar sail deployment system worked as designed. It worked as planned, even after going through all of the vibrations and the stresses of launch, as well as the thermal cycles after being in orbit for a little over 2 weeks, opening up of the solar panels and the change in the spacecraft state that gave us, not to mention all of the ground testing that we put it through before launch, and the fact that it was kept in storage for a couple of years before that. So this particular solar sail and its flight systems has been through an awful lot, and the fact that we could tease this thing into working and deploying as planned, was a real triumph of the engineering team. So in doing that, what we've really tried to do, and we think we've demonstrated, is a very robust and reliable solar sail system that, coupled with small spacecraft like CubeSats, can really open the door to really an entirely new class of low-cost exploration missions. And as Jim and Bill said, that's what's been driving the Planetary Society's interest in solar sailing for all these years. In terms of the spacecraft itself, as you've heard in the past 2 weeks and again just this morning, we've had a number of very serious challenges to deal with. But fortunately, the engineering team found a way out of every single one of them, and now that we understand them, the spacecraft has really been performing beautifully. The spacecraft, as Jim mentioned, is what's known as a CubeSat. So it's very small, and has been compared to, in size, has been compared to everything from a large loaf of bread, a small toaster oven. I've even seen it compared to a 12-pack of beer, if you've ever seen one of those. So it's small. I'm not actually why all of our comparisons have to do with food. I'm not sure. That must mean something. Anyway, weighs about 5 kilograms. I guess that's a little more than 11 pounds. And within that small package, it contains all of the usual spacecraft functions. All of the electronics and batteries and other components are included in the interior of this small spacecraft. And in our case, the solar sail is packed in there, as well as the deployment motor that extends the sail and the booms to which the sail is attached. And on the outside of our spacecraft are 4 small solar panels that flip upward on command to expose the solar sail, and that's how we deploy it when we're ready. So just in terms of the timeline, we opened those solar panels 1 week ago today on June 3rd. And as a matter of fact, it was that change in the state of the spacecraft that triggered what I think was one of our biggest challenges, because the power system then, was in a different configuration with the solar panels extended, and it was not behaving exactly as we planned and expected. Took us a few days to figure out what was going on, and I will say that was some real white-knuckle time for the spacecraft team. We had very limited data to go on. We were dealing with a spacecraft that we knew was in a different and uncertain power state. We were not getting reliable communications. So there were some real worried nights there, sleepless nights. And we also knew that with the panels open, the spacecraft was going to be subjected to greater torques and forces during each orbit, which would gradually start to make it rotate faster and faster. And we saw that happening. We knew that this rotation would eventually become a problem for our communications, as well as for the sail deployment. We didn't know exactly what rate of rotation would really interfere with sail deployment, but that was becoming a real concern. So the clock was ticking, and we were forced to start thinking of some very tough choices. Fortunately, shortly after that, with some really good detective work by the team and a little bit of luck, we began to understand what was happening with the batteries and power system, and we were able to restore communications and get some data back from the spacecraft. So then at the first opportunity, we gave the command to deploy the solar sail. And that actually took place last Friday. The deployment was not successful on that first attempt for reasons that we're still analyzing. We decided to spend a day on Saturday gathering a little more data and trying to get into a good orbital configuration and try again on Sunday. The first attempt that Sunday, this past Sunday, was also not successful. And we really thought we had one more chance that day, and in fact not a very good chance, before things would start to get pretty dicey. But that third time was the charm, and we saw the sail motor start to spin, so we knew that the deployment was at least beginning. Then, of course, just to give a little more drama where we didn't need it, the communication pass ended before we could see the deployment go all the way to completion. So that's why we had to wait until yesterday for the real confirmation, which is the image you've all seen, and that was quite a thrill. So this has really been a roller coaster ride of emotions, a lot of sleepless nights for the operations and engineering team, but they're very dedicated, they're very smart people, and of course getting that beautiful picture of the sail yesterday really made the whole thing worthwhile, so everybody's just very pleased. Just a few words about what comes next. So with all that we've learned a tremendous amount about our flight system and how to operate this spacecraft in space. And even as we speak, we have people on the engineering team using that to help us get ready for the flight next year. So this week's flight is really just a test drive, making sure that the systems are operating, working as designed, or at least we understand how they're working, and that we know how to operate the spacecraft. But as Jim noted, this particular flight is not in a high enough orbit to allow actual solar sailing due to the atmospheric drag, and we knew that before launch. That will come late next summer when we launch a virtually identical spacecraft on our second flight, our primary mission. This one will go to a higher orbit, about 750 kilometers circular orbit, and that will allow us to actually be high enough to conduct real solar sailing on a mission that should last for at least 3 months, maybe as long as 6 months. In that case, next year we're being launched in tandem with another spacecraft that's called PROX-1. That's PROX-1, short for proximity. That spacecraft is being built by students at Georgia Tech. We have one of them on the line here, Kevin Oksiniuk. PROX-1 will actually be able to get up close and personal with LightSail next year while we are in the process of deploying the sail and then shortly afterwards, so we can see it in action. And that is really going to be something. Those should be very spectacular images, and the technical value of those images, seeing the sail in space from different angles, that will give a tremendous boost to our understanding of the behavior of solar sail in space, and that'll be of even greater benefit to the planners of future missions. And really, I mean, that's what this is all about. It's laying the groundwork, setting the stage for those future low-cost missions. And, it's the members and contributors to the Planetary Society that have been so dedicated to making all of that possible. And speaking for the entire technical and engineering team, we're just all very, very grateful to everybody who's made this day possible. So I think with that, Aaron, I can throw it back to you, and we can move on with questions.
Thank you very much, Doug. We will now begin the Q&A period of our press conference, but I first want to review some protocol. If the press can please remember to keep your line muted while you're not speaking, and please speak only one individual at a time. State your name and affiliation, and I will field your questions accordingly. And also just a reminder, on the line at this time, we have Bill Nye, Jim Bell, Doug Stetson, Rex Ridenour, Barbara Plant, Jennifer Vaughn, Jason Davis, and Kevin Oksiniuk. With that, I'll take your questions, and then we'll segue to a Twitter Q&A period after about 10 minutes of audio questions.
Hi, Peter King with CBS News. Can you hear me?
Yes, thank you, Peter.
Thank you, and I guess this question is for Doug. I'm wondering if there is anything immediately that strikes you that you know you need to change for the next mission, and a part two on that is, are you fully funded for the next mission? Thank you.
Well, part two first. I think the answer is yes, we're fully funded. We've had some very generous donations to the Planetary Society, and of course the Kickstarter campaign that's ongoing now has been just tremendously successful. And so I think, these are low-cost missions, but anything you do in space, low cost is a relative term. So, but the answer is yes, we're fully funded and we're ready to go. In terms of things that we know we need to fix, where do I begin? I mean, there's actually a long list. I'd say that some are minor, some are more significant. The two more significant things that we learned from this particular flight, one has to do with our attitude control system, and there's a software issue that cropped up shortly before launch that we identified and we need to fix. In fact, and that particular fix is very simple, and I think Barbara and the software team have already understand what to do. So there's a attitude control system on board the spacecraft that holds the orientation stable. That's not working on the current test flight. We know how to fix that for our primary flight next year, and so that'll be a major contribution. And in fact, it's vital that works properly in order to really do meaningful solar sailing. The second is an issue that I think Jim or Bill may have referred to. There is a software file problem which caused us to lose contact with the spacecraft shortly after it was launched. And again, that's something that we understand. The manufacturer of the software, of the electronics and the software, we've been in touch with them. We know how to update it, and we have a new version of the electronics for our next flight. So those two particular things are absolutely critical, but we've already have fixes in the works for our next flight.
Thank you.
This is Irene. This is Alan Boyle with NBC News. Can you hear me?
I can. Just a quick follow-up to the previous question. I'd like to offer an opportunity for Jennifer Vaughn, our Chief Operating Officer, to provide some follow-up information.
Yes, I feel compelled to say that although we're very close to nearing our finish line for funding, we're not quite there yet. So our budget right now is $5.3 million, and we still have about $400,000 to go on that. And just a caveat there too, that budget was based on what we knew before we flew. So now that we actually know how we performed in flight, we may have to do some revisions that could or may not affect that bottom line. But just wanted to clarify that we're nearing that finish line.
Thank you.
Okay.
And the next name I heard was Irene Klotz.
Karen, for Doug, just wanted to know what the problem was with the battery and how did the team manage to resolve it? Thanks.
Okay, well, I think for some of the details, I'll probably hand this off to Rex Ridenauer from Ecliptic. Just in general, it has to do with the battery charging circuits, and there are certain protections that prevent the battery from getting either over voltage or over current. And we were in a situation in which we were probably getting a little bit of both after the solar panels opened. So Rex, would you like to provide a little more detail on that?
Yeah, hi, thanks Doug. And Irene, in retrospect, we believe the battery system was working as designed, even though at the time it seemed like it maybe was a classic anomaly. But as Doug said, there's actually 8 separate batteries on the spacecraft. Each one has 4 different protection circuits trying to protect it from either over voltage or under voltage or over current for charging or over current for discharging. And as Doug said, when the solar panels were first deployed, we got this big bump up in available power and voltage. And all of that rushed into all 8 batteries at the same time, and the batteries basically started independently responding to that, and we believe some got into a protection mode first, which, as it turns out, causes the others to cascade into similar protection modes. And eventually, the first thing we saw after our telemetry came down from the solar panel deployment was all the batteries were disconnected from the bus, and they were basically offline, which is a little surprising to us. But it took about 2 or 3 days for the battery system to adjust to the new power levels and go through all the eclipses and the sunlit periods and eventually stabilize. And eventually they did stabilize and everything was working great. But all that perturbation really caused some concern. But it really wasn't an anomaly. It was as designed. And it looks like it's working well now.
Thanks.
Thank you. The next name I heard was Alan Boyle. And can I please remind our spokespeople to state your name before answering a question, just to ensure our journalists know who's answering. Thank you so much. Alan?
Yes, thank you. I wanted to ask about what comes up for the rest of this mission. Are there other things that you need to do or are looking to do? For example, there was some discussion about whether the booms would have to be extended more, whether you wanted to flatten out the sail panels, or do you feel as if it really is mission accomplished and you're finished? And also the question of how much longer the spacecraft is expected to last. When do you expect atmospheric reentry to occur? Thank you.
Doug Stetson, could you field that one? Thank you.
Sure. Yeah, sure. Okay, this is Doug Stetson, the project manager. So I'll take the last part of your question in terms of reentry. This we knew going in this would be a short mission. Right now, we expect reentry this coming Sunday. Now, there's a fair amount of uncertainty around that because as the spacecraft gets lower and lower, it will experience different amounts of atmospheric drag. So it could be as early as sometime early this Saturday. It could be late Sunday. That's kind of the window that we're looking at right now, and that gives us about the amount of time on orbit with the sails deployed that we expected. In terms of the remind me of that first part of the question.
Other things that you need to do with the spacecraft,
oh, yeah, right.
For example, is it really fully deployed, or do you need to stretch the booms out more?
Yeah, we do not need to stretch the booms out more. The objective is to validate the deployment system works, and the images that we have, all the data that we have, show that it worked absolutely perfectly. Now, it is conceivable that we could run the motor a few more counts and stretch the sail out a little bit more. We have not decided yet whether we're going to do that. We don't think it would make a significant difference in the appearance of the sail. And certainly what we've seen now is enough to validate full mission success. So from that point of view, we're done. There will be potentially some value in doing an experiment like that in preparation for future missions. Larger, more expensive solar sail missions in the future will probably want to do something like that, in which they deploy most of the way first and then take some measurements and then carefully inch it out the rest of the way. So from the point of view of contributions to future missions, that's one thing that we're considering doing before the end of this weekend. There are other things. We're looking at getting additional images of the other side of the sail, for example. We're considering taking more images from different lighting angles, different background conditions, just to learn as much as we can about the condition of the sail itself. We're also considering cycling the spacecraft on and off. Basically, each time we do that, we get a little bit more data from our sensors. So that all of this is pointed towards learning as much as we can in preparation for our next flight and for the subsequent missions, in future years. So we're going through a process right now to decide exactly how we spend our last few days on orbit, but those are some of the possibilities.
Hello.
I would just like to add something, if I may.
Is that Bill Nye?
Yes. I just want to point out that when he talks about motor counts, in order to deploy the sails to this extent, we had 134,200 revolutions of the motor. And I mention this because I just want to emphasize how compact this mechanism is and how carefully it was designed to pull this off, to have just a 3-unit CubeSat, get sails this big packed in and remain this rigid. There's no mean feat. And so we're talking about hundreds of more counts of this little sort of Swiss watch mechanism. I just think it's fascinating.
Barbara Plant, did you also have a follow-up to that?
Yes, this is Barbara Plant with Boreal Space. Doug mentioned quite a few of the items that we have on our, I would like to call it the stretch goals list, since our mission success criteria have been met. One of the things that we'd like to do is to apply basically what you would call an on-orbit patch to LightSail to try to tease a little bit more information out of our attitude control sensors, especially because when we are in our descent, as we're approaching the Friday, Saturday, Sunday time frame with the orbit, we'd really like to glean as much attitude control information as we can to look at the sail dynamics and be able to write up some papers on that topic and even share data out with interested parties at JAXA or NASA, Marshall, or other folks that we've been in contact with throughout the mission. So that's one big one that I would like to add.
Thank you, Barbara. Next question, please.
Marcia Dunn, Associated Press here. Can you hear me?
Yes, thank you, Marcia.
Yes. What was the initial orbit of the spacecraft? How far has it dropped as of today? And how shy of the 344 square feet do you think the sail is open to?
Doug Stetson, could you please field that?
Sure. The initial orbit was, now I may not remember the exact numbers here, but it was an elliptical orbit, so it's not completely circular. And the highest altitude, it's called apogee, was approximately 650 kilometers. Lowest was about 350. I'd ask Jason Davis, who's also on the line. He's been keeping closer tabs on these since he reports them all the time, so he may want to correct those numbers. And Jason has actually been in contact with some of the amateur observers that have been monitoring our orbit descent, and so he probably has the latest information on the current altitude. Jason, can you add any detail to that?
Yeah, sure, Doug. Today's estimates were a re-entry on the 13th or 14th, which I think you already mentioned, and that's based off of an orbit of 346 by 607 kilometers that was reported today by the Joint Space Operations Command. So that's where we are right now.
Thank you, Jason Davis. We're going to take...
And the last question about how much of the sail is actually deployed vis-a-vis the 344 square feet?
Yeah, okay, so that's, again, that's a good question. We don't know exactly. All we have is the one image to go on. Based on that, and in discussions with the primary designer of the solar sail, who's a gentleman named Chris Biddy, he believes that we are within 90 to 95%, actually maybe a little bit more than that, of what would be considered full deployment. So I have not converted that into, how many square feet or square meters, but it's certainly, if our final, the total area, if it was all stretched out, is, I believe, something like 32 square meters of sail area, then we're probably not more than a meter or two short of that. Now, you have to keep in mind that this is the first time this has been tested in zero gravity. So it's going to behave quite differently than in the ground tests, of course, without gravity, helping to smooth out the folds and kind of hold things down. It's expected that we will see some variability in the sail, some wrinkles. So we never expected it to be completely flat and, stretched taut. That's something that for future missions, I know one of our contributions is to help them understand the dynamics and the process and exactly what they can expect in terms of flatness of a sail, but that was not one of the objectives of our particular flight.
Thanks a lot.
Thank you, Doug Stetson. Next question, please.
Hello, Jonathan Sheldon. Can you hear me?
Yes, thank you, Jonathan. What is your question?
Hi, I'm Jonathan from Space News. I'm wondering, in the 2016 flight, what do you guys plan to accomplish in 3 to 6 months? Where can you go on a solar sail in that amount of time?
Would you like me to take that, Aaron?
Is this Doug Stetson? Yes, that would be great. Thank you, Doug.
Okay. This is Doug Stetson, and I'll give a first part of an answer, and then I'd like to ask Kevin Aksiniak in a moment to say a little bit more about the 2016 flight. But basically, we're not going to go anywhere. We're going to stay in Earth orbit. So this is a relatively small spacecraft with a relatively small sail compared to the sizes that would be required to really venture farther into the solar system. So again, it's more of a proof of concept. What we'll be doing in 2016 is deploying the sail virtually identical to the one that we've deployed this week, and learning how to fly it, and that's a pretty intricate process. That requires fairly precise movements of the sail, changing its attitude with respect to the solar radiation pressure, so that you can gain some momentum from that radiation pressure. So our real objective is to demonstrate the process of regular every single orbit turning the sail to get the most benefit from the solar radiation pressure. In doing that at the particular altitude that we are with our size of the sail, we won't see much of a change in the actual size of the orbit. What we will see is a change in its inclination or the angle of the orbit with respect to the Earth. That's something that's easier to change with a sail of our size. So that will be sufficient to prove that we are actually intentionally modifying the orbit due to solar sailing, and it allows us to demonstrate this process of every single orbit turning the sail to its optimum angle to the sun to get the most bang for the buck, so to speak. So that's the objective. And then, as I mentioned earlier, this is in tandem with a Georgia Tech spacecraft, student-built spacecraft. Kevin Aksiniak is one of the students, and maybe he could say a word or two about the objectives of the other spacecraft that we'll be launched with.
Yeah, this is Kevin Aksiniak here at Georgia Tech. I'm the project manager for the PROX-1 mission. What PROX-1 is going to do is it's going to deploy LightSail, the 2016 LightSail launch from a 720-kilometer circular orbit. Once LightSail is deployed, we're going to command a chase and rest kind of maneuver to catch up to LightSail. We're going to command those maneuvers to be between 50 and 150 meters from LightSail. Then we're going to perform natural motion circumnavigation around LightSail that will be enabled by our set of infrared and visible cameras, along with a series of autonomous proximity operations, guidance, navigation, and control algorithms. And after that, LightSail will open up its sail and we'll be able to image the entire opening process or deployment process for the solar sail and inspect the sail to make sure that it is performing as expected. So that's the concept of operations for PROX-1 as in regards to LightSail.
Thank you, Kevin. We have time for one more phone question, and then we will segue into our Twitter Ask Planetary Q&A period. But I'd like to underscore that we invite you all to follow up with us if you have any questions that go unanswered during today's press conference. And I'd also like to redirect you to the planetary.org website, where we have a LightSail press room set up that has many resources to support your reporting. So one more question, please.
Hi, it's James Dean from Florida Today.
Hello, James Dean. Your question, please.
Thanks so much. I wanted to ask Bill Nye, and perhaps anyone else, if they'd care to weigh in on if you were surprised and maybe a little pleased at how much drama could be packed into such a tiny spacecraft mission.
Well, I wasn't surprised. I've been... How about, yes, I was surprised at how serious the problems were, and they're classic. I have to say, I'm a mechanical engineer. I've worked on a lot of mechanical systems, and I'm of a certain age. I worked on hydraulic systems. And they just have different problems from software. Software is so subtle, and as I understand it, we got into a problem where the software was running for a number of hours, and then a counter or something self-disabled it. And this is the kind of just fantastically subtle problem that can only be solved with testing. And, I'm an old Boeing guy, and we love quoting Tex Johnson, who was the test pilot on the 80, the first 707 airplane. And he said after he did a barrel roll with an airliner. He lands and he said, one test is worth 1,000 expert opinions. And I just can't say enough good things about the opportunity we had to fly this test mission a year before our primary mission. And it just goes to show you how subtle software is. And I'm just so proud of the whole team. And there's one other thing I wanted to add. I've received emails from people all over the world. The people who are enthusiasts, the engineers and scientists who are enthusiastic about solar sailing, it's a little bit of a niche. But I've heard from a lot of people from Europe, the Japanese Aerospace Exploration Agency who flew the Icarus sail, and they're all giving us a big thumbs up because we pulled this off. The Icarus sail is great, but the thing is huge. It was a 600-kilogram spacecraft, and it was not the primary purpose of that mission. Whereas ours is we're just trying to solve this one problem. It's really gratifying. It's a great question. Yes, I was surprised. I was troubled, but I'm proud to know these people. They solved the problems while it was on orbit, while it's flying over at 28,000 kilometers an hour, and the best is yet ahead.
This is Jim Bell. I'll just add, I've been involved with Mars rovers and big NASA projects, and it's really it's not a surprise that problems crop up in projects like this involving space exploration at all scales, whether it's a giant billion-dollar NASA mission or a little spacecraft like ours. And I just echo Bill's pride and delight in our team, our professional engineers, our technical staff, people, students that are involved. This is what Bill and other engineers do. They solve problems, and problems will always crop up no matter what the scale, and it's just been spectacular to see that all happen so successfully.
Thank you, Jim Bell, and thank you, Bill Nye, and thank you, James Dean, for your question. Did we have one other comment from Bill?
Yeah, I just wanted to say, Jim will back me up, that the Spirit rover, which is $1 billion or more than that now, all in, a very expensive NASA mission, you guys had to upload a whole new operating system, right, after it was on the surface just a few weeks into the mission. Is that accurate?
Very, very common to have to learn how to operate your spacecraft when you actually get where it was designed to operate. And that's exactly the situation that we found ourselves in with LightSail.
Thank you, gentlemen. Now we have time for just a couple of questions that we've gathered through Twitter, through our Ask Planetary hashtag. And I'm going to ask Danielle Gunn here at the Planetary Society to field a couple of questions through Twitter. So spokespeople, please stand by.
Okay, our first question comes from Tracy Moody. She asks, why was LightSail not equipped with mirrors or magnifying glasses aimed at the sails to concentrate the energy?
Well, I can quote our beloved fictional engineer, Mr. Scott, who points out that he cannot change the laws of physics. This is to say, even if you put a lens on the spacecraft, it's kind of a cool question. Even if you put a lens on the spacecraft, you're still only going to gather as much light as the area of the lens. So making the bigger sail is the way to go. There'd be losses in the light passing through the lens, and it's not clear that you can make material that would withstand the heat and extra energy if you concentrate. It's a kind of a cool question, but the more straightforward way to go is to build a big sail. Imagine putting a big funnel on a sailboat. You could do it, but you're only going to get as much energy as the area of the open area of the funnel. That's kind of a cool question.
Okay, our next question is from Joseph Urban. Should interplanetary rocket-powered missions add a light sail to increase speed after using fuel?
Rick, you want to try that?
Sure, this is Rex Ridenauer. Going back to Bill Nye's comment, the physics applicable to LightSails pretty much demand that whatever package you're carrying or moving around with the LightSail has to be very, very low in mass. And so for a typical envisioned human mission or a big cargo mission, LightSails of any size really don't apply because the masses are too big. So the reason we're on this path with CubeSats is because we know now that a very small, low-mass CubeSat can do quite a bit, and it turns out you can match a sail size to that mass and actually get some good propulsion out of it. But anything much bigger than these CubeSats right now, you would need a much larger sail, and we're just not there yet. So you got to keep everything really small and low mass to move it around with a sail.
Thank you, Rex Ridenour.
This question is from Christian Peel. Have you considered making all source code and other design documents open source?
Rex, maybe for you also, or Barbara?
Yeah, this is Barbara Plant with Boreal Space. That, in my mind, would be totally up to the science guy in the Planetary Society. We have the design documentation, we have the source code, and I guess we should put it to them to discuss it and make that conclusion.
Yeah, I'll just add that, the vast majority of the spacecraft subsystems, as with most CubeSats, one of the advantages is that they are widely available. And there's a lot of small companies now that have grown up to build CubeSat components and the software that goes along with them. So that all is the stuff that we used. I mean, there's no secret to that. So they're highly available. That's one of the big advantages, as Bill mentioned earlier. CubeSats can democratize space exploration, and putting a solar sail on it means they can do more and more things. So all of that information, all of that tech capability is generally available now, and that's really a big step forward. That's why we're so excited about the potential of this marriage of CubeSats and solar sails.
Yeah, this is Jim Bell. Barbara mentioned that their desire is to publish some papers and results from what we've seen. That'll be out in the literature for anybody to access. And I think that if our mission can help enable others to mount similar missions or improve upon the technology, I think that's a win for everybody.
And that's our mission at the Planetary Society, to help everyone advance space science and exploration.
Thank you, everyone.
Our next question's from Drew Faber. What makes communication so difficult when passing over a station?
Doug Stetson, could you please field that?
I think actually I'd ask Barbara, probably has more experience, to answer the particulars of that in our case. You want to try that, Barbara?
Sure. Again, this is Barbara Plant. We're dealing with essentially radio frequencies in the amateur bands, UHF, VHF. So there's some properties of being in that band that sometimes get a little iffy. Atmospheric disturbances, bad weather, but also from the aspect of space, if one has any rotation inherent to the spacecraft as we're passing over. And we've seen a little bit of this with our LightSail test flight, that the ground controllers can see, the slight fade in, fade out of the signal. So again, the properties of the spacecraft, the physical properties of it rotating, and LightSail did start rotating faster in one axis after our swings through perigee. We learned a lot about that behavior, and certainly the folks at Cal Poly and Georgia Tech handled that admirably on the ground side.
In fact, this is Rex Ridenour. To put some numbers on it for those interested, when we came out of the ejection mechanism from the rocket, our highest spin in any axis was around 7 degrees per second. And over the next 10 days or so, that built up naturally to about 15 or 16 degrees per second. after we deployed the solar panels, just the 4 solar panels, we dropped down to about 10 degrees per second maximum spin. But then those panels, we believe, served as basically little propellers during perigee passes. And we were building up a rate of 6 degrees per day, roughly 5.5 to 6 degrees per day. So by the time we finally popped the solar sail out, we were spinning up around 32, 33 degrees per minute, which was one of the concerns Doug alluded to, is that we didn't want to keep increasing up to 60 or 70. We didn't know what would happen. So as soon as we popped the sail out, the aggregate spin rate of the entire spacecraft dropped way down to like 3 degrees per second, which is what you would expect in the ice skater analogy. We threw the arms out and everything slowed down. So that was a pretty dramatic piece of evidence that we successfully deployed the sail when the spin rate came down.
Thank you very much. We have time for one more question and then our closing remarks.
Our final question comes from James Knox, who sends his congratulations, and his 11-year-old son Landon would like to ask Bill Nye, how far could the LightSail travel in the solar system?
Well, if you read my predecessor's textbook, Lou Friedman's textbook, you could send it as far as you want to. Just keep in mind, the farther you get from the sun, the less light you have. And if you're twice as far away, you only get a fourth or half again as much light. Nevertheless, if you have time, you could get as far in the solar system as you want. And then if you like to think big, like really big, what we do is put a laser on the far side of the moon, and then you'd make a LightSail huge, just a huge one, and you'd beam the laser beam at the LightSail at every convenient time from the moon, and you'd push it all the way, let's say, to the next star system. And you power the laser with the solar panels on the surface of the moon, for example. And this is an exotic idea, but it is, if you think about it, the only really usable technology to get to the stars. And so it's an inspirational thing, and this is why we've worked really hard to use LightSail, to advance the LightSail technology, not to go to other stars, but there's some missions for which a LightSail is perfect. And one of them would be to keep an eye on the sun and see when there's what they call solar weather, when there are big mass ejections from the sun. A solar sail spacecraft could monitor that and warn us here on Earth, but not have to orbit as fast as, say, the planet Venus, because it would be held out against that being close to the sun gravity by this pressure of photons. It's a great idea. And then, of course, we also have proposals it is also interesting to note that we have proposals to use solar sail spacecraft to look for asteroids. So since the Comet Halley mission in the 1970s, people have proposed using solar sails to go out and catch up with these distant objects. So right now, there really isn't much of a limit on what you can do in the solar system. And this LightSail test flight is the first small step on that long journey. That's a great question.
Thank you very much to our presenters today, our experts on the line, and thank you, media, for joining our call today. If you have any follow-up questions, please don't hesitate to contact us, and please do visit our website, planetary.org, and visit our press room for reporting resources. Thank you again for joining us.